Welcome to Welding Technocrat YouTube channel. Today, let's discover how engineering critical assessment ECA ensures structural safety and reliability by analyzing flaws using advanced fracture mechanics principle. What is ECA engineering critical assessment? Engineering Critical Assessment (ECA), also known as fracture analysis, is a specialized procedure that applies fracture mechanics principles to determine the defect tolerance of safety critical components. Unlike traditional code-based acceptance criteria, which often rely on arbitrary limits for flaw size and toughness, ECA provides a fitness for purpose approach. This means that instead of assuming all flaws are dangerous, ECA evaluates whether a specific flaw can exist safely under given loading conditions. It considers factors such as brittle fracture, fatigue, crack growth, crack growth, and plastic collapse. By doing so, ECA helps engineers make informed decisions about structural integrity, repair needs, and inspection interval. This approach is widely used in industries like oil and gas, nuclear, aerospace, and power generation, where structural failure can have catastrophic consequences. ECA ensures that safety critical items such as pipelines, pressure vessels, rigs, and wind turbines operate reliably without unnecessary repair or replacements, thereby saving costs and enhancing safety. When is ECA used? ECA is applied at different stages of components' life cycle to ensure structural integrity. During design stage, ECA assists engineers in selecting appropriate welding procedures and inspection techniques, ensuring that the design accommodates realistic flaw tolerances. In fabrication stage, ECA evaluates the significance of known defects that do not meet fabrication code requirements, determines maximum critical flaw sizes, and assesses minimum fracture toughness or maximum operating stresses. During operation, ECA becomes crucial for assessing flaws discovered in service. It helps decide whether these flaws can safely remain in place or if repair, downrating, or replacement is necessary. This structured approach allows industries to avoid unnecessary interventions while maintaining safety standards. By applying ECA at these stages, companies can optimize maintenance schedules, reduce downtime, and extend the life of critical infrastructure without compromising safety. Information required for ECA. To perform an ECA effectively, specific information about the component and the flaw is essential. First, detailed flaw characteristics such as size, position, and orientation must be known. These parameters influence how the flaw interacts with applied stresses. Second, accurate stress data for the region containing the flaw is required, including operational loads and residual stresses from welding or fabrication processes. Third, material properties such as fracture toughness and tensile strength are critical for predicting failure modes. Gathering this information often involves a multidisciplinary approach combining stress analysis, non-destructive testing, and material engineering. Advanced techniques like fracture mechanics testing (CTOD), J-integral, K, and finite element analysis (FEA) may also be applied to refine the assessment. This comprehensive data collection ensures that the ECA provides a reliable evaluation of structural integrity under real-world conditions. Standards and methods. ECA procedures are standardized in several internationally recognized codes to ensure consistency and reliability. Key standards include BS7910, which provides guidelines for assessing flaws in metallic structures, API 579-1 ASME FFS-1 for fitness for service evaluations, and the R6 code used in the UK nuclear industry. These standards outline methodologies for determining flaw acceptability based on fracture mechanics principle. Analytic methods often involve fracture toughness testing such as CTOD, J integral, or stress intensity factor measurements. For complex loading conditions, finite element analysis (FEA) is employed to predict crack tip stresses, residual stresses, and collapse loads. FEA also helps determine whether lower constrained specimen can be used for toughness measurements. In addition to static flaws, ECA can assess growing flaws caused by fatigue, creep, or stress corrosion, enabling life extension and safe inspection planning. These standardized approaches ensure that ECA remains a robust and adaptable tool across various engineering sectors. Tools and expertise. Performing an ECA requires specialized tools and expert knowledge. Decision support softwares like CrackWise is widely used to streamline flaw assessment in accordance with BS7910. These software assists engineers in evaluating the integrity of pipelines, pressure equipment, and structures containing flaws. Advanced non-destructive testing techniques, fatigue and fracture testing facilities, bespoke testing procedures for aggressive environments further enhance the accuracy of ECA. Expertise in these areas ensure that the assessments account for real-world conditions, including the adverse effect of corrosive or high-stress environment. In case where standard methods are insufficient, custom solutions such as full-scale testing or specialized finite element modeling may be implemented. These combination of advanced tools and multidisciplinary expertise enables engineers to deliver precise and reliable evaluation of structural integrity. Benefits of ECA. The benefits of ECA extend beyond safety assurance to include significant economic and operational advantages. By accurately determining whether a flaw is critical, ECA prevents unnecessary repairs and replacements, reducing maintenance cost and downtime. It enables confident decision making regarding flaw significance, which is essential for planning inspections and life extension strategies. ECA also enhances the safety and reliability of critical infrastructure, minimizing the risk of catastrophic failures that could endanger lives and cause environmental harm. Furthermore, ECA supports compliance with international standards, fostering trust and credibility in engineering practices. Overall, ECA is a cost-effective, scientifically grounded approach that optimizes resource allocation while maintaining the highest safety standards. Happy welding! Thank you for watching. Kindly like the video and subscribe the YouTube channel Push the bell notification for new welding related videos. Share the video with welders, welding foremen, welding engineers, and welding enthusiasts.